Hi, this is Mark. In this video, I'm going to derive pi, or 3.1415 dot dot dot. This set of video segments, it's going to just be about deriving different equations or relationships, mathematical relationships. For anyone interested in knowing, where these relationships were derived, and I've always been very interested in solving equations or finding equations or deriving them in different ways. I think math is, it's about exploration. It's an art, and it's an art form. It's poetic. When you get up into the upper level, you basically search for patterns and other relationships, and that can be distributed in all avenues of life. I mean, every area, every domain that you get into has a different set of these relationships, and math is just one small area that is quantitative, an analysis. But I'm going to start here with, if you draw pi, or if you want to find the area of pi, it's essentially you take a circle and you let the radius, so you're going to let radius, which is just r, let it equal to 1. So what you want to do, I didn't draw perfect, but hopefully I can get it clear here. So if you construct into 4 segments, you draw a perpendicular line pointing through, crossing the midpoint. And what you do is you connect each of the outer nodes together. And what you find is you have a square. You have a square in here which is composed of 4 triangles of right triangles. So if you take this initial right triangle, quadrant 1, you notice the radius is 1. So using the Pythagorean Theorem, a squared plus b squared, you notice that this is going to be the square root of 2. So what you do is you have the area total. We know that this equals to the square plus 4 times, essentially. Now we have these half circles or segments, but we connected the node. If you actually notice how we connected the node, each of the nodes has been connected at 0. Like if you do degrees, it's 90 degrees, 180, and this is 270. You know that notice that this is a 90-degree angle, and the interior have to be equal to 180. This is going to be a 45-degree angle. So what you notice, if you draw a circle, what you end up having is actually this is equal to a square if you connect the outer. So if you take the midpoint right here, and you're projecting the diagonal through the midpoint, you end up having a set of more triangles. I didn't draw perfectly. So, and now you have new semicircles. So originally, notice how we have 4, which is equivalent to 2 to the 2 squared power. Whoa. Every time you break it in half, you're breaking it into 2 more sections. So iteration 1, we have number of triangles. Let's say number of triangles equals 2 to the 2 squared. So equals 2 to the 1 plus 1 power. But then we have, if we have iteration 2, number of triangles is 2 to the 3 power, which is going to be 8, and so forth. So basically you have number, if you keep going in this succession pattern, you have 2 to the I plus 1, where, or not times 1, but plus 1, where I equals iteration number. So that's the key here, but we need to know how to find the triangle. We need to construct this angle right here. But you notice one thing. This is r, which equals a 1. So let me show you the diagram. So notice how you have this semi-circle, and it's horrible drawing. So basically, what I did right here is, of course, we have this segment, and we're trying to find this angle, but this angle we know is 45. Well, if we project this logically, because due to symmetry, you know, when you have a circle, you notice a few things. If I draw a line like this is like y equals x. It's symmetric on both sides, basically equal dimensional. So if I do a line like this, if this is a subset of R, it's basically this is like delta x. Well, this is delta x, or you know, it's delta y really. Actually, we call it delta y. We have delta y is delta x due to symmetry. But we notice right here is for this segment right here, if we drew an angle, like if we draw another triangle right here, and we project this point down here, and we draw a triangle right here, and we project it right here, notice how this original triangle y equals x, we know that delta y equals delta x for line y equals x, of course. But if y is greater than x, notice how if we go beyond this point, this is delta y is greater than delta x. So like if we represent this as quadrant 1, and this half is quadrant 1 and this half is quadrant 2. So on quadrant 1, we have delta y is greater than delta x. But in quadrant 2, we have delta x greater than delta y, but in the same equal dimensional way. So basically, right, with this, you know, if we're going to project this line, if it hits the midpoint of this segment, for it to be equivalent or symmetric on both sides, we have to have this distance equal to this distance. Has to be true because they have to be symmetric on both sides. And if it weren't the case, if I shift this over a little bit, this has to be shifted down and this becomes greater. So they have to be equal. And the only way is if, you know, x is going to be r over 2. And we have y equals to r over 2. It's just half. It's half the distance of this whole trend. And that's just going to be 1/2. This is going to be 1/2. So the key relation there is because it's half, we know that the angle, theta, so what we're looking at right here is, we're constructing again. So basically we have a line here, midpoint here. This angle right here, theta, let's just say 45, theta 1. So theta 1 is just going to be 45 divided by 2 to the 1 power. And then we do another, and we're dividing in half. Well, now that's going to be 1/4, and 1/4, it's cutting. So now we have theta 2, which is 45 divided by 2 squared, 4, because it's 1/4. And then we keep doing this, is theta I is 45 divided by 2 to the I power. So that's the key there. We know we can relate these triangles as a function of theta. So now we know originally this base is root 2. So basically, for the triangle, the first triangle, this is 45 over 2. This is going to be root 2 over 2 because it's half. It's cut in half. So, provided we have that, we can solve for, let's just say this is let's just say this is B. So let's just say this is B1. So essentially, we know that this is 2, this length right here is because it's going to be cut in half again. This is 2B2. We'll call this 2B2. And we'll call this H1. So using this, these relations, it's key. You can build an iterative formula, and you can use that like using geometry, or you can use trigonometry, and like the angle. Like if we take the sine, or remember SOHCAHTOA. So the sine is opposite over hypotenuse. So basically we can create this relation. Like if we want to get h, we know that sine, for instance, this is, let's just call theta I, or theta 1. We know that this is equal to opposite, which is h1, over 2b2. But we don't know that, but we also know cosine theta 1 is adjacent, which is b1 over 2b2. Which we know because b1 is root 2 over 2. So therefore, if we reduce this, we know that 2b2 is just b1 over cosine theta 1, or just as root 2 over 2 divided by cosine 22.5. So that's the first iteration. So basically now that we solve for this, and we can also use tangents. Instead of using sine, we can use tangents theta 1, remember y over x, so we have h1 over b1. So basically with this formula, we already know b1, so h1 equals b1 tan theta 1, which is root 2 over 2 tan 22.5. So using this iteration formula, like if we do iteration 1, so we know the area, we're doing 4 times, of course, this is just the area of a triangle is what? 4 times, or essentially now we're doing how many triangles? So we have 8 actually. This is going to be 2 to the 3 power times the we have b1 h1 over 2. But to generalize this, we have 2 to the essentially, if this is iteration 1, this is actually, I think before, what did I do? This should be I plus 2. If we're starting with iteration, if we're starting with iteration 1, and then it's going to be 8 initially because we divided it into 8 triangles, and that's going to become 16, and then it's going to become 32, and it's 2 to that. You said your iteration plus 2, and then you take the summation, or this should be the summation term screwed up there. This should be the summation of I is 1 to n, 2 to the I plus 2, and then this is bi hi divided by 2. Now we divide it by 2, so basically you take the summation of I equals 1 to n. Because you divide by 2 in this, it becomes 2 to the I plus 1. bi hi. And, you know, if we're looking at these relations, you know, we have h1 is bi tan theta I. So we're given like bi, we'll start with bi. So 2 bi plus 1, so we have 2 bi plus 1. And looking at this, we have bi plus 1 is bi over cosine theta I. So basically, notice how this is cosine theta I. So essentially, if we're going to take, for instance, so that means bi plus 1 is this bi over 2 cosine theta I. So in this case, if we're going to constrain it to starting at 45, so we can change the formula right here, and we can make it the integral of theta is 45 to theta theta equals 45 over 2 to the I, and basically we're going to have 2 to the I power. No, it wouldn't be 2 to the I power, it'd just be so essentially, yeah, this is we could just, we'll keep it right. So this is theta equals 45 over how would I put it? 45 over 2 to the I, 2 to the n power. So essentially this, we could relate it, if we're starting with I as 1, or this is I plus 1, and this is just going to be bi hi. So essentially, if we start, like, if we're going to take the iteration or the formula, so we do iteration 1, so just say I1. Well, we know initial angle, theta 1, is 22.5. And we know that B1 equals, or B2 equals, it's B1 over 2 cosine 22.5, which is just root 2 over 2 divided by 2 cosine 22.5, whatever that is. And we can get this value. So we know B2 already. And we know that H1 equals, H1 was B1. What was it? So we have H1 is B1 tan theta 1. So it's just B1 tan theta 1, which is root 2 over 2 tangent 22.5. So we have the iterated formula, so we know that area 1, we're doing 2 to the 3 power times, in this case, we have root 2 over 2, because that's just B1, this is B1, and times H1 is root 2 over 2 tan 22.5, and basically that will give us A1. So if we do the iteration 2, we already know B2 or B2. So essentially, we can use we can solve for the B3. And this is just going to be 22.5 over 2. So we're plugging in already. We solved for B2. So up here, and we input that to get B3, and then H2. We already know that this is root 2 over 2 over divided by cosine 2 cosine 22.5, and remember this is tangent 22.5 over 2. So basically H2 was BI, which is B2, times tangent theta 2, which is just going to be 22.5 over 2. So if we give that, and you can solve B3 and use basically you do I3, you continue, but this is going to be the area. We know it's going to be 2 to the 4, and we have B2 H2, and you keep going on, and as you keep progressing, usually I think if you reach iteration 9 or so, it's just approximately equal to pi. It's so basically it converges very fast to pi, I believe in like 6 or so iterations. So there you have it. That's the way to, if you want to derive pi. You can do it geometrically as well. It can get more a little bit more rigorous, but of course there's many ways to solve pi. And then for the next video, I was going to go over the derivation of the circumference. So pi, I mean, of course, it's just the area with a circle with radius 1. Pi r squared, pi times 1, of course, it's going to be pi. But it's basically the cool thing about pi. If you go back to the if you go back to the, if you draw like this, or not a great drawing, but we have 4 triangles right here. And then you create 8 triangles. I kind of skipped an iteration, obviously, to go into the 8 because I took care of the square. But yeah, you have 8 iterations. Or you have 8 triangles, and then you have 16. So you have 4, and then it becomes 8, then it becomes 16, becomes 32. It's doubles, right? It keeps doubles. It's times 2. Times 2, times 2. So basically, and this goes on to infinity. So the area is, you take, let's just say a triangle. Times essentially, or you're taking how would I put it? It's the summate 0, or you go 0 to infinity of each triangle. But the funny thing, the key, I'll just say this is the area. A is the area of the triangle, and then of course you do 2 times. This is 1 to infinity, so it's 2 to the I plus 2, so forth. So essentially, or 2 to the I plus, you start with actually 4 triangles. So 2 to the squared. So you have infinitely many triangles. But the triangles, you start with a larger triangle, and then it gets cut smaller. And then it gets cut smaller and smaller. So you can, if you relate the triangle dimensions, you eventually you go from here 1 1 root 2 this triangle, and you keep going until you reach a point, essentially. Very, very infinitesimally, or however you say that, small triangle. So it converges. So basically, if you relate this as a function, and we have area, what is it, area of the first triangle. So 1 root 2. Base times height divided by 2. So the area of this is this going to be 1/2, or 1/2. Of course, the area of the square that we determined before, the area of the square is 2. That's just 1/2. That's just 1/2 times 4. So we start with 1/2, and you're converging to 0. So the limit so basically this is we can think of this. So that's the area, and we can relate this with one of the variables. Let's just say base b. So this is a b-axis. So the base is getting smaller of area I. So as base approaches, or in this case, it wouldn't be base, it would be segments. So basically this is I iteration. So not b, this should be I approaches infinity of AI is essentially 0. So this is just a limit, basically, as you keep going down this, as you keep going towards infinity. What it's saying is, as the iteration keeps, the area becomes approximately 0. So there you have it. It's just that it just shows convergence, and that's why this area converges to pi, because areas as iteration increases approaches 0, and you're taking the summation, and the summation has to converge to 0, otherwise it will diverge. And hope you enjoyed. That's all I have right now, and hope you enjoy, or I look forward to creating the next video which will be on the derivation of the circumference of pi, of a circle.